Stand-Up Physicist. This is the fifth of 6 shows developed to some lectures that I gave at MIT's Independent Activities period entitled Unifying Gravity and Electromagnetism by Analogies to Electromagnetism. People always want to know, well, why haven't people done this before? Well, in today's lecture, hopefully we will show you why. Because the really bright folks who worked on this before got to the wrong answer really quickly and then moved on. But since I'm less bright, I kind of stuck for a long time saying, you know, there should be an answer to this. Because we have one answer, and we're just trying to generalize this a little bit more. We're trying to make it apply to a situation which involves not only space, but just a little bit of time. And it took me a while, but I found the solution to that issue. And we will discuss forces. Things like stresses and geodesics, which are like the easiest path out there to follow. So we start with solutions to field equations. We look at Newton's field equations and the kind of properties it has, and then to solutions for 4D wave equations. That will lead us to this problem area, which we will get around to by using normalization and perturbation, looking at how things vary when you normalize and perturb something, and hopefully end up with a good result. So we start with solutions to field equations, specifically Newton's field equations, and then we do the 4D wave equations. We will see a big problem with those types of solutions. But with the power of normalization and perturbation, when we start to look at variations in that, we can see the right sort of dependence on distance that we need to get. So what are Newton's field equation solutions? Well, you start with Newton's field equations itself. It's that triangle squared phi equals 0. You need to guess a phi that will work there. And if you've studied enough physics, you'd guess a 1 over r. Because you take the derivative of that, and then the second derivative of that, and you add up all those things together, and we've got some things that are negative, some things are positive, and whammo, they all cancel each other out perfectly. This solution has 2 key properties. First of all, if you take the derivative of a 1 over r potential, you get a force law, which is 1 over r squared, an inverse distance dependence. And that is the type of force law for gravity. That's really good news. What's not so good news is that this potential has a singularity. That in itself is not so bad. Mathematicians can often deal with singularities, but it's the type of singularity. And this is a point singularity. So it's kind of like there's a problem and it's only at one point and you're probably not going to be able to do anything. And people have known about that problem like almost since this equation was known. And so it's an old problem. So people are not as upset about it. But it is a problem, and it'd be great if we could kind of come up with an alternative that avoided a point singularity. Let's look at solutions to the 4D wave equation. The 4D wave equation now goes from a triangle to a box squared because it has 4 sorts of derivatives inside of it, and instead of a scalar potential, it has actually 4 vector potential, which has 4 parts inside it. We again need to guess a solution. So we try a 1 over distance, but this time we need to include time. And a way to do that sounds reasonable is to put in time with a minus sign in there. because that ends up being an invariant distance in space-time. But we need to actually use a 1 over distance squared potential. We take the derivative, we take the second derivative, and we put that all back in the field equation, which puts the second time derivative in positively and all the three space ones in negatively, and amazingly enough, that equals 0. So this has a really good property. The really good property is that the singularity is the light cone itself, where every single particle that has no mass lives. So we are going to be able to do a lot of things with this singularity. In fact, it might just nicely connect with the Maxwell equations, which govern how light moves. But it has a huge problem. That problem is that if we take the 1 over distance potential and take its derivative, we end up with a force equation. And that force equation has a 1 over distance cubed relationship. And gravity is not a 1 over distance cubed force law. So I think bright people quickly reach this conclusion and move on. But I think there's a way around this problem. The reason I did the Newtonian solution is we know that's physical. We know that if we only consider distance, we end up with the correct form of an equation. So if we somehow take the smallest step away, then we might be able to end up with an equation that's physically relevant. So to take the smallest step away, we are going to use normalization and perturbation theory. It's almost a cliche in quantum mechanics that when you have a weak field, you normalize the potential and you study the variations. Normalizing appears in the standard model, that U of U1 means that it's got a norm of 1, the S in the SU2 and SU3 means it's got a norm of 1. Nature apparently likes 1. And it's also dimensionless, which is a good thing. And then there is perturbation theory, which is a slight step away, where you take a K, a spring constant, make sure it's small, and study that. So now we look at a normalized perturbation solution to the 4D wave equation. We start with the 4D wave equation, which had that 1 over distance squared sort of dependence. And then we normalize it. And if you really normalize it, you end up with 1. It's not very interesting. But now we take that 1 and we take slight steps away from that 1, presuming that that spring constant is really small. This will be a solution to the field equations, because we really haven't done too much to the equation. We divided it by one number, and then we just studied some small variations. And if you actually go through the math, well, it looks more complicated than the previous solution, but it's a solution nonetheless. We want this to apply only to gravity, and only when gravity is weak. Unified field theory has its own kind of technical hassles, and that is that electromagnetism always wants to join in. So how can we choose a potential such that it really is only about gravity, not at all about electromagnetism? Well, we notice a couple of things about this normalized perturbation solution. The first is that that K, that spring constant, could be either plus or minus. If it is plus or minus, it doesn't change the fact that it is a solution to the field equations. However, it does change what the derivative of the potential is. So I play this game where I now have two potentials. And sometimes the k's are the same sign that adds up, and you get to see that term when you take the derivative. Or sometimes the signs are opposite each other, in which case they cancel each other out when you take the derivative, and it does not appear with the derivative of the potential. So this is the diagonal simple harmonic oscillator potential that will give us a description of gravity and not electromagnetism. This is perhaps the most complicated expression I've written in my entire life, and it was necessary to do so that this is only about gravity. We now take the derivative of this very complicated thing, and we only keep terms to first order in the spring constant K. When we do that, so many things drop out. As a matter of fact, all you are left with is this factor of K over the distance squared, which has the type of distance dependence we absolutely must have. And it is multiplied by the Minkowski metric. That's that +1 in the corner followed by the -1s on the diagonal. So it took a lot of work to find this particular expression. But it looks like it's physically relevant because the derivative of this complicated potential has the right distance relationship. But you can see that it would be easy to overlook such a complicated looking potential. So that's why I think this hasn't been done before. Now we will think about forces, specifically stresses, the Lorentz force, and geodesics, which are like the easiest way to go. So a stress tensor is an object that describes the energy, the momentum, and the stresses involved in a field. It's a second-rank tensor. How do we derive it? Well, as with everything else, you start with the Lagrange density. Then what you do is you take the derivative of this, and you end up with two terms. In the first term, we're actually going to take the Euler-Lagrange equation and rewrite it just a little bit. And for the second term, we're going to rearrange the partial derivatives. The reason for these two is we can now shrink this down using the chain rule again into this one expression, which is a second-rank tensor that we then take a derivative of. Now the stress tensor is defined as the stuff inside there minus the Lagrange density. And so that is the definition of a stress tensor. So what is the stress tensor of this gem Lagrange density? Well, you write out the gem Lagrange density, making sure that we drop those current coupling terms because they just make things more complicated. And then we've got our definition, so we simply apply it, and we end up with these results. Quite frankly, I'm a little confused by them at this time, because in electromagnetism you can calculate the stress energy tensor, and it's got an E squared and a B squared, but they both have positive signs. This doesn't quite work out that way, and I'm not sure what all the consequences of that are, but I've been able to do the calculation, and so that's important. We now move to the Lorentz force of EM. This is a force that tells us how to move around electric particles in a relativistic kind of manner. And it has a cause term. That cause term is the electric charge in motion, or current, that gets contracted with the antisymmetric field strength tensor. This equals the effect term, which is just the change in momentum with respect to the interval tau. If electric charge were to go from plus Q to minus Q, then the sign of this force equation would change. That indicates that there are two sorts of electric charges, as we do see in nature, a plus charge and a minus charge. Because this force equation has a plus sign in front of it, it means that like charges repel each other. Now we use the gravity to EM analogy, just as we did in the very first lectures as part of this set of 6. We have positive electric charge go to negative the square root of g times m, mass charge. We change the antisymmetric tensor to a symmetric tensor, which also requires that we go from exterior derivatives to covariant derivatives. And we just kind of plug all that in. So you can see that we have the cause term, which is now the mass charge moving, or the mass current, contracted with a symmetric tensor. And that equals the effect term, which is the change in momentum with respect to the interval tau. If we were to go from a minus m to a plus m, then we would see that none of the signs would change because there's an m on both sides. The force equation has a minus sign in front of it. That indicates that like mass charges will attract each other, which is in fact what they do. So this is a very good feature of the force equation. Now we form the GEM force law simply by adding these two together. And we see the cause term looks, well, a little complicated. But that's because we have to couple electric charge in motion with an antisymmetric tensor and the mass charge in motion with a symmetric tensor. Nothing changes at all about the cause term. It's still about momentum changing with respect to the interval. We can imagine what it will be like if there is no electric charge. Then we get back exactly the force law for gravity. But for the EM, you never have an electric charge that has absolutely no mass. So we simply have to imagine what it's like if the mass charge is very, very tiny compared to the electric charge, in which case you get back the Lorentz force of EM. And if you kind of do some number calculations, you'll find out that in fact that is very much the case. We turn to geodesics, which are the easiest paths in space-time to follow. We think first about geodesics on the effect side of the equation. That would be the side with the change in momentum. You use the chain rule to break it into two parts, the usual kind of MA term and the other term which has to do with change in mass with respect to space-time. And we suppose that that term equals 0. Then you apply the chain rule to expand the acceleration term, and you get that term that's got a couple of u's in it. But because that is the covariant derivative in there, we apply the definition of the covariant derivative to now have this expression where we see an acceleration term and a term involving curvature. So if there is no external force on this in this system, then any acceleration we see will be due entirely to curvature. Kind of cool. Now we think about geodesics on the cause side of the force equation. So we write out that the cause side and we imagine that it's 0. And then we again kind of use the definitions. of what a covariant derivative is in order to get an expression that's got those Christoffel symbols in it. And the thing that we notice is that there is a mass snuggled right up against that Christoffel. That's very important because it shows that mass couples to curvature. What that kind of means is if mass goes to zero, that Christoffel just goes away. That's not the case if electric charge goes to zero. That term will still be there. But we can also see that we can end up with zero if those potentials are not zero and they nicely balance the curvature itself. And here is where we are fundamentally different from general relativity. General relativity is exclusively about curvature because it is a theory only about gravity. My proposal is a unification of gravity and electromagnetism. We had to find a compromise between potentials and curvature, and this expression kind of does that. Now we need to consider symmetries in the force law, and these are known as killing equations. And it's nothing more than kind of looking through and trying to figure out what's not going to change. If you look at the Lagrangian, you can see that it doesn't have time and it doesn't have any angles in it. And therefore it's going to conserve both angular momentum and energy. And these will be our killing fields. And so we just kind of write them out. I'm not sure exactly what to do with this, but I'm glad we've done the calculation. So what have we accomplished? Well, I think we can understand why other people have cruised on by this area of research. It took quite a bit of effort to find a potential that only applied to gravity, not at all to EM, and had the correct distance dependence of the derivative of that potential. But we found it. We can work with it. And we've examined forces. General relativity really doesn't work with forces as it happens in this theory. In general relativity, it's only about geodesics. And here we strike a balance between potentials and the geodesics. And so it may be an area where a lot of work can be done. Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
It is very difficult to do theoretical physics because everything you try to do has been done before. So you have to practice your imagination every single day. And so every day I pretend that I am a seal. And I love fish. Woo! Woo! Even better, two fish. Or. It'd be even better if I had a ball. Come on, give me the ball. Give me the ball. Oh, that's right, there's nobody else here. I'll go get it.
Or.